Problem number 3. Air flows steadily at the rate of 0.5 kilograms per second through an air compressor, entering at 7 meters per second speed, 100 kilopascal pressure and 0.95 meter cube per kilogram specific volume, and leaving at 5 meters per second, 700 kilopascals and 0.19 meter cube per kilogram. The internal energy of the air leaving is 90 kilojoules per kilogram greater than that of entering. Cooling water in the compressor jackets absorbs heat from the air at the rate of 58 kilowatts. Now, compute the work in kilowatts.
So, the same thing, the same procedure. Let's list down our given and divide it into two states. So, state 1 and state 2. Alright, so I'm going to divide this one into two states. So at my state 1, we have speed or velocity is 7 meters per second. Pressure 1 is 100 kilopascals. My specific volume is, I'm just gonna write it just like this, and it's 0.95 meter cube per kilogram. And my state 2, my velocity 2 is equivalent to 5 meters per second. My pressure 2 is, the pressure 2 is 700 kilopascals. The specific volume 2 is 0.19 meter cube per kilogram. And then the question is, and the internal energy of the air leaving is 90 kilojoules greater than of entering. So meaning, specific internal energy 2 is equivalent to specific internal energy 1 plus 90 kilojoules per kilogram. Since it is greater than, it's 90 kilojoules per kilogram greater than my specific internal energy 1. And cooling water in the compressor jackets absorbs heat from the air at a rate of 58 kilowatts. So my heat is, since it's absorbing, it's rejecting heat, it's cooling. So that means the sign convention of my heat would now become negative. So negative 58 kilowatts. And now my task is to compute the work in kilowatts. So work is unknown. I have my given mass, which is mass flow rate, which is 0.5 kilograms per second. So these are the values that I'm going to work with in order for me to solve for my work. So let me just draw the illustration. Since the same thing as the previous problems, the elevation is not specified, therefore the illustration looks like this. Okay, so this is my state 1 here and my state 2 here. Now I'm going to start with my energy equation. So energy equation is potential energy 1 plus kinetic energy 1 plus U1 plus EF1 plus Q is equivalent to potential energy 2 plus kinetic energy 2 plus U2 plus EF2 plus work. Solving for my work, I'll be transposing other variables to the other side. So the general equation for my work will now become potential energy 1 minus potential energy 2 plus kinetic energy 1 minus kinetic energy 2 plus internal energy 1 minus internal energy 2 plus EF1 plus Q. Plus EF1 minus EF2. This is EF2. And then plus Q. Now since elevation is not specified on both ends, so therefore my change in potential energy is 0. So this will be 0. And kinetic energy, the velocities are given, it's not negligible, so I'll be solving for kinetic energies, internal energies, and change in flow work and heat is already given, so I'll be solving only for 6 variables. So I'll start with my kinetic energy 1. So kinetic energy 1 is defined as 1 half mass 1 velocity 1 to the power of 2. Since mass 1 equals mass 2, so I'll be using the same mass, which is 0.5 kilograms per second. So 1 half times 0.5 kilograms per second multiplied by my velocity 1, which is 7 meters per second to the power of 2. And simplifying that one, so I have 1 half multiplied by 0.5 kilograms per second, and then 7 times 7, that would be 49, so 49 meters squared per second squared. Now I need to create a unit of force times a unit of distance, and then all over a unit of time. Time. So in order to do so, I am going to combine kilogram meter per second squared in order for me to create Newton, and then multiply it by the remaining meter unit, and then dividing it by seconds. So kilogram meter per second squared, that will be Newton. So first I'm going to multiply the constant. So 0.5 times 49 divided by 2. That means the resulting answer value is 12.25 kilogram meter per second squared. That would be Newton, times the remaining unit of distance, which is meter, all over seconds. So that means kilogram meter squared per second squared, kilogram per second times meter squared per second squared is equivalent to Newton meter per second. And Newton meter is joules. So this will become 12.25 joules per second, and joules per second is watts. So I'm just gonna put watts here at the open close parenthesis watts, and converting watts into kilowatts. So since we are solving our work in kilowatts, so 1 kilowatt here at the top and 1000 watts at the bottom. So this would be cancelled. So the remaining unit, my kinetic energy 1, will be in in kilowatts. So 12.25 divided by 1000, that is 0.01225 kilowatts. Alright, so that's for my kinetic energy 1, and now I'm going to proceed to my kinetic energy 2. Kinetic energy 2 would still be the same here, and the only thing that would change is the velocity 2. So I'm gonna put 1 half mass 2, since mass 2 equals mass 1, velocity 2 squared equals 1 half times 0.5 kilograms per second, then multiply this one by our velocity, which is 5 meters per second squared. Therefore simplifying that one, so 1 half times 0.5 kilograms per second, then 5 times 5, that will be 25, so 25 meters squared per second squared. Alright, and the same thing earlier, combining the units, and in order for me to create a unit of force times distance all over a unit of time. So let me just simplify the constants first. 0.5 times 25 divided by 2, that is 6.25. So 6.25 Newton meter per second, or I'm just gonna directly input this one as joules. So 6.25 joules per second, I'm just gonna put it as directly as watts, and then converting watts into kilowatts. So 1 kilowatt all over 1000 watts, just like that, cancel watts. I'm left with the unit of kilowatts. So kinetic energy 2 is equivalent to 6.25 divided by 1000, that is 6.25 times 10 to the negative 3 kilowatts. That's 10 to the negative 3 kilowatts. Alright, I have the value of my kinetic energy 2. Now I'll be solving for my internal energy 1 and internal energy 2. So internal energy 1 is constant, because we don't need to solve for internal energy 1. It is because we are only gonna base it to our internal energy 2. So the energy 1 equals unknown, and then internal energy 2 is equivalent to internal energy 1 plus 90 kilojoules per kilogram. Just like that. We're just gonna put this as is, and we are going to convert our internal energy 2 into specific internal energy 2 into internal energy 2, and also internal energy 1. So internal energy 1 is equivalent to mass times, not like this, but the big one, the big U, times mass times specific internal energy 1, and the internal energy 2 is equivalent to mass times internal energy 2. So I'm gonna put it like this, and I'm gonna substitute the value of U2, which is U1 plus my mass would then become I'm just putting U1 here, since if I distribute M to specific internal energy 1, it will become this form, M times specific internal energy 1. So I'm just gonna use this variable, the big U, in order to lessen the space. So I'm just gonna put U1 here, and then I'll plus mass times 90 kilojoules per kilogram. I have a mass of I'm just gonna show it just like this, times 90 kilojoules per kilogram, just like that. And then I'm gonna simplify it. So U1 plus my mass is 0.5 kilograms per second, and then multiply it with 90 kilojoules per kilogram, and cancelling out the unit of mass, which is in kilograms, I'll be left with 90 kilojoules per second. So my internal energy 2 is internal energy 1 plus 0.5 times 90, that would be 45. So 45 kilojoules per kilogram. We know that kilojoules per second, we know that joules per second is in watts. Therefore, kilojoules per second, that would be kilowatts. So therefore, my internal energy 2 is internal energy 1 plus 45 kilowatts. So I've already solved for my kinetic energy 1 and 2. My internal energy 1 and 2 are already done with. So the only things that I need to solve for are my flow work 1 and 2, and then substitute the values to solve for my work. So let's solve for the internal and the flow work 1. So flow work 1 is equivalent to pressure 1 volume 1. And now we already have a value for our pressure, which is 100 kilopascal, but we don't have a value for our volume 1. In order to solve for volume 1, we need mass and density, but we don't have a given value for density. As you can see here, we don't have a value for density, but we do have a value for our specific volume and 1 and specific volume 2. So the reverse or the reciprocal, since if you're going to do dimensional analysis, the specific volume is in meter cube per kilogram, which is in volume per mass. So if you're going to do the reciprocal of specific volume, it is going to flip, and then it will become kilogram per meter cube, which is mass per volume. So that means we can deduce that the reciprocal of density is specific volume, and the reciprocal of specific volume is density. So therefore, we already have a clue on how to solve for our volume 1. So let's start first with our density. So density 1 is equivalent to the reciprocal of specific volume 1, which is equivalent to 1 all over our specific volume is 0.95 meter cube per kilogram. And as you can see, this is in the form of the division of fractions. And what we're going to do is kilogram will flip to the top, will become our numerator, and meter cube will become our denominator, which is in the form of mass over volume. That's why it is in density. So, simplifying, we'll have kilogram here, kilograms all over 0.95 meter cube equals 1 over 0.95. 1 divided by 0.95, that is 1.0526 kilograms per meter cube. Alright, so since we already have our density 1 and we already have a value for our mass, we can now solve for volume. So volume 1 is mass 1 all over density 1 equals, our mass 1 is 0.5 kilograms per second, and our density 1 is 1.0526 kilograms per meter cube. We can now cancel kilograms, and then division of fractions, meter cube will flip to the top. So volume 1 is equivalent to meter cube per second. Simplifying, 0.5 divided by 1.0526. So the resulting value is 0.4750 meter cube per second. Alright, so we already have our volume 1. Now we can solve for our flow work 1. I'm just gonna put it at this side in order for me to save space. So flow work 1 equals pressure 1 is given as 100 kilopascal. So 100 kilopascal. So if I'm just gonna write first kilopascal, and I'm gonna show to you how to break down that unit. And then volume 1 is 0.4750 meter cube per second. And what I mentioned is I'm gonna break down kilopascals. Kilopascal is the result of the units Newton per meter squared. Since it is, Pascal is the result of Newton per meter squared. That means kilopascal is the result of kilonewton per meter squared. Alright, so if we substitute if we reduce this one to its simpler form, it will become 100 kilonewtons per meter squared. Multiply this one by 0.4750 meter cube per second. Cancel meter squared. We are left with kilonewton meter per second. We know that kilonewton meter is kilojoules, and kilojoules per second is kilowatts. So we can directly input this one as kilowatts. So 100, there's no need for us to convert anymore. We're just gonna multiply the constants. 0.4750, so it's 47.5. So kilonewton meter per second, that is kilowatts. So 47.5 kilowatts. That is for our flow work 1. So remember, Newton meter is joules, joules per second is watts, and kilojoules per second is kilowatts. So that's for EF1, and now I'm solving for my EF2 the same way how I solve EF1. So pressure 2, volume 2. Solving for volume 2, we need our density 2. Solving for density 2, the reciprocal of our specific volume 2, which is 1 all over. Specific volume 2 is given as 0.19 meter cube per kilogram. Alright, just like that, and it will flip, will be given by the reciprocal. So kilogram will go on top, and then 0.19 meter cube will go at the bottom. We can now solve for our density 2, which is 1 divided by 0.19, and it's 5.2632. 2632 kilograms per meter cube. Alright, so I'm gonna put it at this side in order for me to save space. Solving for volume 2, So volume 2 is equivalent to mass 2 all over density 2. We already have these values, so we can now directly substitute the value of each variable. So mass 2 is 0.5 kilograms per second, and then density 2 is 5.2632 kilograms per meter cube. Cancel kilograms, meter cube will flip to the top. That means we will have, simplifying this one, 0.5 all over 5.2632. The volume is 0.00995. Because it's 9499, we are going to round that off, and then the unit would be meter cube per kilogram. Alright, so this is our volume 2. And the next thing we would do is apply the formula for flow work 2, which is pressure 2 volume 2. The same thing as what we did here on the EF1. So pressure 2 is given as 700 kilopascal. I'm just gonna input directly kilonewton per meter squared for kilopascal, and multiply this one by my volume 2, which is 0.095 meter cube per kilogram. I mean, not kilogram, not meter cube per kilogram, but meter cube per second. I'm so sorry about that, because we are canceling kilogram and kilogram, so meter cube will flip to the numerator, so meter cube per second. So we can now cancel meter squared from the meter cube, so we'll be left with kilonewton meter per second, which is a unit of kilowatts. That means EF2 will now become 700 times 0.095, 66.5 kilowatts. Right? So we have already solved for our unknowns. Now we can use these values that we have arrived to solve for our work. Now work is, the general equation for work is kinetic energy 1 minus kinetic energy 2, this one, kinetic energy 1 minus kinetic energy 2, plus U1 minus U2 plus EF1 minus EF2 plus Q. So we'll start with our kinetic energies. So kinetic energy 1 is 0.01225 kilowatts, minus our kinetic energy 2 is 6.25 times 10 to the negative 3 kilowatts, plus our internal energy is, internal energy 1 is unknown, so I'm just gonna put the variable U1, and then I'm gonna deduct this by my internal energy 2, which is U1 plus 45 kilowatts, just like that. And then next is my EF1 plus EF1, which is 47.5 kilowatts, and then minus my EF2, which is 66.5 kilowatts, and then plus my heat, which is in negative, because this is the heat, the heat is being rejected through cooling water compressor jackets, so which is in negative because this is the heat, the heat is being rejected through cooling water compressor jackets, so this will become negative 58 kilowatts. And here's the thing, there's actually a clue in which you are going to be able to know that if you are correct or not. If ever you are solving for compressor problems, air compressor problems, the heat should always be negative, because compressor rejects heat and also receives work. So therefore negative heat and negative work. So the answer of this the answer here, if I simplify these values, should be negative. If ever it will become positive, therefore there's something wrong with my solution. So that means all of this, if I simplify all of this, I need to have a value of negative work. So because that is the nature of our compressor, it receives work and it rejects heat. So negative work and negative heat, always remember that. So I'm going to simplify this one now. 0.1225 minus 0.01225 minus 6.25 times 10 to the negative 3, and then minus u1 u1 minus u2, so this will become I'm just gonna put it here, u1 minus u1 minus 45 kilowatts. So this will be its resulting equation. So that means u1 will now be cancelled and we'll be left with negative 45 kilowatts. So negative 45 minus negative 45, and then plus 47.5 minus 66.5, and then minus 58. So the resulting answer would be negative. So it's negative 121.994. Therefore, I'm on the right track. So negative 121.994 kilowatts. That means the work received by our air compressor is negative 121.994 kilowatts. That's it.